Okay, so 2.2, basic rules for differentiation. Okay, so your quiz on Friday is on your derivative, your definition of derivative. So the x plus delta x definition. It's on the alternate form of the definition of derivative, which enables you to find the derivative at a specific point. And lastly, being able to write the equation of a tangent line. So I like point slope form, and we know that the slope of the tangent line is the value of the derivative at the point of tangency. Okay, so you have to be able to use the limit definitions, evaluate it, use our algebra techniques from chapter 1. But now we have all sorts of rules that eliminate the use for the definition of derivative when we're attempting to do any type of problem. Let's see. So each of the following are theorems for derivative rules. So the derivative with respect to x of any constant number. All right, so c is any real number. It's just simply 0. So for each theorem, I'm just going to show you a few examples. So if I give you f of x equals 2, and I ask you for the derivative of 2, the derivative is just simply 0. F of x equals square root of 3, the derivative of that is just 0. F of x equals e, where e is the irrational number approximately equal to 2.718. The derivative is just 0. So in this course, we'll never use pi or e as variables. Okay, these are represent the irrational numbers. We know pi is about 3.14, and then e about 2.7. All right, our next theorem. This is your bread and butter. The derivative with respect to x of x to the n power. This is what we call our power rule. And we'll use this more than any other. So the derivative is n times x to the n minus 1 power. So look at what we've done. The original exponent, you bring out front of the term and then subtract 1 from the exponent. F of x equals x to the 7th power. The derivative of x to the 7th, 7 times x, 7 minus 1 gives me to the 6th power. F of x equals square root of x. So I can rewrite this as x to the 1/2 power, the rational exponent. So the derivative, bring the exponent out front, multiply it by x, and then subtract 1 from the original exponent. So 1/2 x to the negative 1/2 power. Now I will require that you write the positive exponents. So the derivative would be 1 over 2x to the 1/2, or you can write it as 2 times the square root of x. But I do want to see the exponent be positive. F of x equals 1 over x squared. So the goal is to rewrite every expression in this form, x raised to some power. So I can rewrite my original as x to the negative 2nd power. Now using the power rule to find the derivative, bring the exponent out front, subtract 1 from the original exponent, negative 2x to the negative 3rd, and then writing that with a positive exponent, negative 2 over x cubed. So the power rule is a very useful, it's the most useful one. Think about the definition of derivative with these. You would have to take x plus delta x and expand it to the 7th power, or every time you wanted to find the square root of x, the derivative. Using the definition, we would have to rationalize the exponent, or rationalize the expression. So that's why these rules eliminate the use for the definition anymore, because the definition just becomes too labor intensive or something that we're not able to expand ourselves. Okay, the next theorem. the derivative with respect to x of c times f of x, where again c is just a constant value. So the derivative, c remains, that's our coefficient, and we just multiply that by the value of the derivative. So if I ask you for the derivative with respect to x of 3x squared. 3 is my coefficient to my function, so that's going to just be multiplied by the derivative of x squared. Now using the power rule, bring the exponent down, subtract 1 from the original exponent, so the derivative would be 6x. F of x equals 2x to the 5/6 power. 2 times, applying the power rule, bring the exponent out front, x, subtract 1 from the original. So now I get 5/3 x to the negative 1/6 power, and just rewriting that with a positive exponent, 5/3x to the 1/6. And then lastly, if I gave you pi over 2 x to the 4th, I would rewrite this as pi over 2 x to the negative 4th power, and then applying the derivative, pi over 2 times negative 4, subtract 1 from the original exponent. These cancel to negative 2, negative 2 pi x to the negative 5th, and then the last step just to make the exponent positive. And I do have to correct this. This is my function. This is not equal. I would say then I start with the derivative and I apply the rules. Okay, the next, if I have the derivative with respect to x, if I'm adding or subtracting functions together, then I can just find the derivative of the first function and add it or subtract it to or from the derivative of the second function. Now this is really useful because what it says, every rule, the rules that we just went through, the derivative of a constant being 0, your power rule, and the derivative of a constant times a function. Now we can use these individually and then just add what each of the values of the derivatives together. So f of x equals x cubed plus 5x squared minus 3x plus 8. I can look at these individually as 4 separate functions, and to find the derivative, I just apply the appropriate rule to each term. X cubed, the derivative of x cubed using the power rule is 3x squared, plus derivative of 5x squared, 5 times 2 gives me 10x, subtract 1 from the original exponent. The derivative of negative 3x, let's talk about that for a second. This is raised to the first power, so using the power rule, negative 3 times 1, x to the 1 minus 1. So this becomes negative 3 times x to the 0, and we know anything to the 0 power is 1. So the derivative of negative 3x is just negative 3, and then the derivative of any constant term is 0. Now the more and more you use these, I won't have to see the plus 0. So our final answer for the derivative, 3x squared plus 10x minus 3. So I'm actually going to add, using this rule, the derivative of a constant times x, all right, x to the first power, is just the coefficient, because anytime we subtract 1 from x, or excuse me, subtract 1 from 1, we get the 0 power. And again, we know that that's equal to 1. All right, f of x equals x squared plus 5 minus 3x to the negative 2. So using each of our rules individually, derivative of x squared is 2x. derivative of a constant term is 0. The derivative of negative 3, x to the negative 2. Negative 3 times negative 2 gives me positive 6 as my coefficient, x to the negative third power. So rewriting this with positive exponents. Now once you get here, you're not required to get a common denominator. So keep them as separate terms. Alright, it's easier for me if you've made a mistake, I can find where it is, and you'd never have to combine them on the AP test. So keep them as separate terms as you're doing the work. Okay, let's look at, if I give you the function x cubed minus 6 divided by x squared. The only rules you have are constant, power rule, x raised to some power, coefficient times a function, and the only other derivative rule we can use is if we're adding or subtracting functions. Well, this has a division in it, so you don't have a rule to find that derivative yet. So what we need to do is split the numerator, so separate the rational expression into two fractions, and now I can rewrite, and notice we'll be using the power rule on each of these. So x cubed divided by x squared gives me x, and then I'm going to rewrite the second term with a negative exponent. So now when I go to find my derivative, I have a rule that applies. So if f of x is x minus 6x to the negative 2, then when I find the derivative of x to the first power is 1 plus 12x to the negative third, and then just writing that with positive exponents. Alright, if you have something that looks like this, 3x times 6x minus 5x squared. Again, you don't have a derivative rule if you're multiplying expressions. So algebraically, what can we do? We can distribute the 3x. F of x equals 18x squared minus 15x cubed. Now each of those individually is just the application of the power rule. 18 times 2 is 36. 2 minus 1 gives me x to the first power. 15 times 3 is 45, and 3 minus 1 gives me to the second power. Okay, the last two rules are your trig derivatives. So the derivative with respect to x of the sine of x, and the derivative with respect to x of cosine of x. So your homework tonight is to prove these two derivative rules. Okay, so the derivative of the sine function is the cosine function. The derivative of the cosine of x is negative sine of x. And you're going to prove that using the definition of the derivative. So limit as delta x approaches 0, sine of x plus delta x minus sine of x all over delta x. And then for cosine, to find the derivative, limit as delta x approaches 0, cosine of x plus delta x minus the original function all over delta x. So notice both of these derivatives are going to require these expansions. Sine of the first, cosine of the second. Keep the operation the same. Cosine of the first, sine of the second term. And then the cosine of x plus delta x. Cosine of the first term, cosine of the second term. Switch the operation, sine of the first term, sine of the second term. So that's your homework. Prove those derivative rules.